Well, here's an example that's somewhat challenging example. Simplify the integration by use of Jacobians with a change of variable. The region R, and this is what makes this so hard, is the square with vertices pi 0, 3 pi over 2, pi over 2. There's pi 0, 3 pi over 2, pi over 2, that's here. Pi pi, that's here. And pi over 2, pi over 2, that's here. So those were listed in order. And our function is f of xy is x plus y squared times sine of x minus y, the quantity squared. We could call it sine squared of x minus y, but my software won't write it like that, but that's what it's intended to be. So an obvious choice would be to let u be this and let v be this. So now the integrand will be simpler because it'll look like f of uv equals u squared times sine of v squared. See how much nicer that integrand is now. But we'll have to remember that the Jacobian that we will find will also be a factor of our integrand. So there'll be some other thing, we don't know what yet, that'll be a factor of the integrand. And so what we're actually doing from this, I could show you that. So what we're going to do is actually find, if you can imagine the diamond over here in the same position as this is in, and by the way, notice how high up this function gets in a few places, right? What we're going to find is actually the volume underneath this goofy looking surface and above this diamond in the xy plane. Now, I can't draw the diamond perfectly, but I think you can see going from maybe pi over 2 here, this is the point pi pi, and this is the point somewhere up in here is the point pi pi, maybe up here, and over here is the point 3 pi over 2, pi over 2, and down here is the point pi over 2. I wonder why X could be a little better than it is. Three pi over 2 is, oh, that's my problem. Okay, one time out here. I give them a quick plot data and say that's got to go clear out to 4 point something or other. 9 pi over 2 has got to go way out to there, and oops, I got to make the blue one go out there too. 9 pi over 2, I'm approximating it with 4.5. I know it's a little bit bigger, but so here's what we're going to be finding. We're going to be finding the diamond, which I'm trying to draw right here, right? Pi to here to here to here, and we're going to find the area under this graph over the diamond. Okay, so a natural change, as I'd already pointed out, was let u be x plus y and v be x minus y, and then our function is just u squared times sine squared of v. And if we have that in the equations, x plus y equals 2 pi, which is the equation of this line, and x plus y, which equals pi, which is the equation of this line. See, this gives us a top and a bottom. Now we must be real careful here, because the top would be this one and the bottom would be this one. And so actually I did this wrong and could not understand why I was getting a negative answer for the volume that I showed you, and I just kind of rethought this. This is actually the bottom, and this one's actually the top. And so our V should be going not from 0 to pi, but from pi to 0. So I made a mistake first time I did this, and I think I caught myself and figured out what the error was. Everything else is pretty smooth sailing, I believe. So we need to solve the system since x plus y equals u and x minus y equals v. then we can solve by determinant. X plus y equals u, and x minus y equals v. The determinant of the coefficient matrix is here, 1, 1, negative 1, negative 1. So that's negative 2 in the denominator. And replacing the x column with the vector uv, we get negative u minus v, all that over negative 2. So it's both will wind up being positive. So x equals half a u plus half a v. Similarly, we can get y, the coefficient matrix still at negative 2, and so this is v minus u, so you can probably see v minus u over negative 2 gives us negative a half v plus 1 half u. And so when we look at the Jacobian of these two, partial of x with respect to u is 1 half. Partial of x with respect to v is also 1 half. The partial of y with respect to u is 1 half, and the partial of y with respect to v is negative a half. So when we find this, calculate this Jacobian, it's negative a fourth minus 1/4, so negative 2/4, which is negative a half. And so our integral becomes this very nice integral, negative u squared sine squared of v times the 1 half. Actually, that's the negative 1 half. That's where this negative sign came from. U going from pi to 2 pi, and v carefully going from pi to 0, remembering which one was on the top. Right? 0 is on the top, pi is on the bottom. So, all right. So hopefully you see that. It took me a while to figure that out, trying to figure out why I was getting a negative answer. So now that we've set up this integral, which is a very easy one to do, I would say, well, let's take this half and flip these two limits of integration back around, and we'll go ahead and integrate u squared, of course, is u cubed over 3, but it's going to be u cubed over 6 because of the 2 that's there, so that's that. And u going from 2 pi down to pi, so that's going to be 8 pi cubed over 6 times sine squared of v minus 1 pi cubed over 6 times sine squared of v, so therefore it's going to be 7 pi cubed over 6 times sine squared of v. Now, and the question is, well, how are we going to integrate sine squared of v? And the answer is, don't you remember that when you want to integrate an even power of sine and cosine, you have to use a trig identity. So the trig identity is actually a variant of the double angle formula for cosine, and it's really 1 minus cosine 2v over 2. I took the 2 and combined it with the 12 that I already had there, so therefore I just need to integrate 1 minus cosine 2v. This is just a constant after all. So integrating 1, we get v, and integrating cosine of 2v, we get sine 2v over 2 times this constant, of course, and the limits of integration are 0 to pi, so when I put in pi here, actually, I think you see that I get 0, sine of 2 pi is 0, and when I put in 0, this is also 0, so, and when I put in 0, this is 0. So therefore, the only thing that's going to come out of this is the pi from this, putting in for this v, times this 7 pi cubed over 12, so we wind up with an answer of 7 pi to the 4th over 12. I think that's somewhere in the neighborhood of 50-something, 56 maybe, I don't know. Let's give an approximation of that. And approximation, 57, closer to 57. And go back and look at our picture and see, does this look like the volume above the diamond, right? And look, this part of the diamond is almost right on the plane, and so is this part. So it's kind of only the part that juts up here that's very large. Does that seem reasonable that the total volume under there is 57? I would say certainly does seem like a reasonable answer for this, because there's not much volume in this part. It doesn't get big till over in here. So yeah, that seems like a reasonable answer. And again, here's what we are finding. This diamond here, right? And Actually, that's not a very good diamond there, because that's going from 0 to 3, and I don't, yes I do, I do want the y to go from 0 to pi, that's right, y goes from 0 to pi. X goes from about pi over 2 to about 3 pi over 2, and I was just calling that 4.5, so yeah, that's very good, so that's what we found.